Okay, so this is my crash course primer for you on how to analyze the data that you collect. So what I've got here is a sample data set, which I've erased most of the items from, but I've got enough here for us to work from. So your data analysis has 4 basic steps here. 1, check the raw data. 2, compute your scales. 3, check your scales. And then 4 is where you get on and analyzing it. So we'll just roll through that more or less in order. And this is the strange voice that people adopt when they're recording things where they start saying, we'll do this and we'll do that. So I'm already feeling a little self-conscious, but life is okay. So number 1, checking your raw data. So when you download your data from Qualtrics or wherever you get it from, if you use Qualtrics, you can actually export it into SPSS directly. You can choose to download SPSS data, and so it arrives looking something a bit like this, although the variable labels are usually a bit less coherent. They're usually Q_273 or something like that. So I've already done some translating here. So the first thing that you do when you get your data is you want to just SPSS has 2 tabs here. There's variable view, which lists the variables, version, time to do, loyal1, loyal2, merge, mat, SWB, and it tells you the width and how many decimal places and a label. Often it's very helpful to put a label in here. Qualtrics will download your data with very strange names and labels, which, if you've used labeling of the questions, will actually give you a useful label. Values, they sometimes have them. So it might be something like this. Which product value could be 1 if it's a phone, and add, and 2 if it's other. I think this data set I mostly have 1 as a phone, add. Okay. And the other thing that you want to get right here is make sure that scale, you've got the right kind of question. So they can be scale, ordinal, or nominal, and that's something you learned about in your class, so you want to make sure you've got the right one. For the most part, it's not vital, but it's worth checking. So if I go over here and I find which prod, right, this is the one I labeled. There's a tag button here called value labels. If I click that, it now shows me my labels: phone, 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 other, phone, 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 other. I think I asked people if they had a phone, and if they said no, then I asked them about something else. So these are, most people had phones. And you can click off the labels here. So it switches back and forth between a number and the word. Now you might ask, why am I using numbers at all? Why don't I just put in the word phone or other? And the answer is SPSS isn't very good at coping with strings. It isn't very good at coping with strings of letters like Samsung or iPhone or ZTE. It does much better if you say, which data should I analyze? Everything where which product is equals to 1. It can do that. If you say everything where the string includes Android, it'll get confused. So generally speaking, if you've got conditions that you manipulate, that people get one condition or another, you want to code those as 1 and 2, or 0 and 1, or 1 and -1. It doesn't ultimately matter what you choose, what numbers you choose. But if you give it numbers and then put a label on it so you can remember which is which, but that's generally the most helpful way to go around doing it. So let's think, what else do we want to do here? So first of all, it's worth just inspecting your numbers to get familiar with it. And then look for what kind of hits you. So sometimes you see a bunch of missing data here. Here you see there's no phone number, and then you look and you go, right, that's because they weren't asked about phones. There's no loyalty scores. That's because those questions asked about how loyal you were to your phone. There were different questions about how you asked how loyal you were to some other product. So that's right. Whereas this same person does have scores for materialism and these personality variables and gender that everyone was asked about. it looks like this question is blank, and if you scroll down, you'll see that they pick up here. This is because I'd started running this data set, and then I realized, hey, wait, I could ask them this other question, and I added it to my Qualtrics survey halfway through. So data suddenly starts halfway through the data set for this one question. And so you can actually see things like this hard-coded into your data set. Let's see what's going on here. So yeah, you can see people who have done things. You can see questions that were on very different scales. So you can see this demand scale, you're getting 59, 49, whereas all these other ones are 1, 2, 3, 1, 4, 8, 3. This one has -2, -1. And so if you know what your questions are, you can think about whether that's a sensible thing that should be there, or whether it's some kind of mistake. And mistakes do happen. So I had a survey once where I looked at the data, and some question that should have been 1 to 9, the numbers went 1, 2, 3, 1, 3, 4, 5, 15, 1, 3, 5, 19, and it just jumped out at you, these 15, 19, and it turns out that Qualtrics had regarded 1 as 1, 2 as 2, 3 as 3, 4 as 4, 5 as 5, and then 6 as 17, and 7 as 18, and 9 as 19. So once you knew that was there, it was pretty easy to correct. So let's look at these menus. There are 3, other than file, you use data, transform, and analyze. Those are basically the only 3 tabs that you're going to use in your analysis. So you can go to transform, and somewhere in here you can go recode into same variable. And so if something like that has happened, you could say, let's say demand, we've got a problem. You can say all the new values, and then you can say, okay, if I'm seeing 15, that really should become a 5, because it's supposed to be a 5. And you add that. And if there's a 16, that's supposed to be a 6. And we'll add that, and then continue. And then if I press OK, it'll carry out that transformation. And I'm not going to do that because that's not really the case in my data set. But this is one kind of problem that you can very much solve if you spot it. And so it's worth having a look at your raw data to see things like that. Right. So having looked at our data and decided that it's okay, we can start trying to compute our scales. Because when you get it, you will have, and I've cut it off here, you'll have something like materialism 1, materialism 2, materialism 3, materialism blah, 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 and you might have 15 different materialism items, but you don't want to try and analyze those separately where the 15 different items all predict things on their own. You want to combine them all into one. So this is step 2, computing scales. Now, the way you do this, remember our 3 tabs, data, transform, analyze. The first option under transform is compute variables. So we are going to compute a new variable. We can give it a name. We can call it whatever we like. Let's say mat for materialism. And then we can scroll down the list and find our first materialism item. And then we can scroll down and we can find, oops, let's put a space in there. You can find another materialism item, and you can go on. Now, on its own, we've got an equation here, materialism equals, and then this thing, right? Now, let's say that there were 3 materialism items only. Oh boy, I put it in the middle. Let's say there were 3 materials, so you can just type in here. You can type in stuff directly. You don't have to go through the drag and drop menu. One way to calculate and average them all is you can just type it in like an equation. This, whoops, plus, where's plus? This, plus this, and then say divide it by 3, and that will compute materialism, an average of those 3. But there's a problem here, which is sometimes, you can see over here, someone will have not answered a question. So if I took the average of those three, 8 plus nothing plus 7, and divided it by 3, I would get a loyalty score that was much too low, right? Because the average of this person's loyalty scores is really 7.5, but if you added 8 and 7 and divided it by 3, it would be 15 divided by 3 would be 5. So there's a trick to avoid this, which is there's a built-in function for calculating means. So you just type mean. Oops, I made it caps. Doesn't really matter if it is or not. And then you comma, get rid of that. So if I type mat or materialism equals mean of mat 1, mat 2, and mat 3, it'll compute the mean for me, and if there's missing data, it'll divide it by the right number. Now, I could press OK, and it would calculate that score for me right now, but there's this button that you will come to know and love right next to OK called paste. If I click paste, change existing variable, I already have one called materialism, I'll say OK. You get this syntax window. Syntax is the commands that, if I dataset activate dataset 1, and it puts that at the beginning, don't read that unless you open several different datasets at once, which you're not going to do. It says compute mat equals mean, mat 1, mat 2, mat 3, and this is just a text file. You can add for mat 4s, mat 5s, although you've got to make sure you don't make mistakes and forget an underscore or something. And then you say, if I want to compute a new scale, I can cut that and paste it and paste it and paste it, and then say this new one will be BESC, and then I can even put spaces in so it all lines up better. Equals, and you can put in BESC 1 and BESC 2, and things like that, and then each one ends in a full stop. And here's how this works. I'm going to give this a different name. Mat, kill me, BESC, kill me, just so I remember to delete it. And we'll delete that. So I highlight those, and then also the execute, because otherwise if I don't highlight execute, it'll just sit there and it won't do anything. And then I push this green play button, run selection, and it goes bonk. And if I look at my data set, over here it's added a variable on the end. It should have done. Oh dear, what's going on? Output. Whoops. It says incorrect variable name. Aha. Aha. Oh yes, so I've told it variable names that don't exist, and that's why it's throwing an error. So let's just go back to my syntax window, and we'll get rid of this. And we'll... This is what you find yourself doing a whole lot, is running stuff, and then it throws an error, and you go, what? Why did it throw an error? And then you go back and look at it and work out why. So if I run this here, okay, Matt kill, and here it is, Matt kill me, and if I go to data view, here it is. And I'm going to delete it now because it's not a real scale. But that's the beginnings of how you compute a scale. Now, there's another wrinkle. I'm going to open up an Excel file here. So here is the materialism scale. These are the names that Qualtrics gave it. I just cut and pasted it from the SPSS into Excel. This is the actual items. So materialism, 15 item. Number 1 is I admire people who own expensive cars and homes. And number 2 is some of the most important achievements in life include acquiring material possessions. Item number 3, I don't place much emphasis on the amount of material objects people own as a sign of success. Now, if you look at it, this question is reversed. It's phrased backwards. If you're very materialistic, you would say, yes, 7 out of 7. I admire people who own expensive cars and homes. But then when you get to this item, you'd say, I don't put so much emphasis on the amount of objects people own. If you're very materialist, you'd say, no, 1, I disagree. So if I just took a straight average of this highly materialist person 7 and their 7 and their 1, it would give me a score somewhere in the middle of the scale, and that doesn't reflect who this person is. This person is a materialist. They need to have a high score to this reversed item, not a low score. So I need to flip their items. Now, if you look at it, there's an easy trick for reversing items. So if items are scored 1, 2, 3, 4, 5, 6, 7, I need to turn that 1 into a 7, and that 2 into a 6, and that 3 into a 5, and so on. If you have a 7-point scale, and you do set it as 8 minus that score, let's move this over. Here, I'm going to say 8. And I'm going to set this as equal to 8 minus 1. That's for 7. Whoops. Yeah. 8, right? So let's paste this here. Turns out it works perfectly. So this number needs to be 1 more than the maximum number of scales in the item. So if it's a 7-point scale, you use 8. If it's a 9-point scale, you use 10. If it's a 5-point scale, you use 6. Because 8 minus 1 is 7, and 8 minus 7 is 1. So it's this neat trick to perfectly reverse the items. So I can delete those now. So what I've done is, if you look at this, I've pasted in something here that flags with an asterisk which items are reversed. So this one is reversed, this one is reversed, this one is reversed. Now, trying to type out all of that syntax for all of those lines gets really tedious if you've got a whole lot of scales and a bunch of subscales in them, because these are subscales. S is success, C is centrality, H is happiness. These are subscales of the materialism scale. So here's my trick for making them really quickly. You use Excel, you have compute, and then you copy and paste that down a bunch of times, and then a name like mat1, mat dash, and then in Excel, the quick way to make consecutive numbers is you write 1, 2, and then if you grab the bottom right corner, there's a dot, and if you grab that and pull it down, and it's only the bottom right corner, it continues the pattern for you. So it fills in the 1, 2, 3, 4, 5, 6, 7, 8. So then, you can grab those names and paste them in here. And what I'm doing is I'm spelling out the syntax that I need. And here's the magic. There's this function called concatenate. And so I'm going to concatenate this cell and this cell, comma, this cell. I'm just typing commas between these, comma, comma. And you can see up here that this is what I've typed out. And then we'll put a close bracket on the end, enter. And what it does is it just pastes all of those cells into one string of letters. So compute mat1 equals q23 underscore 1.1 close bracket, and that full stop to end the line. Don't forget the full stops. You'll find you forget the full stops a lot. This will be a frequent reason that your code breaks. So you paste these, cut and paste it, and here I've now got a bunch of syntax made. So if I copy that and then I open up my syntax file here, and I paste it in, I've got a bunch of pre-made syntax for me that would have been very, very tedious to type out by hand. Now, notice I did something else here, which is I have this flag for items that are supposed to be reversed. So what I've done here is on the ones that are supposed to be reversed, I put in an 8- there, so the line comes out reading compute mat3 equals 8 minus q23 underscore 3.0. And I've just made sure that on the lines which I need to reverse them, I put my 8- there. So my new scale that will be computed will happily reverse all of the items just as if needed. Now, so if you look at this, all this code is doing here is turning Q2311, which looks like junk, into materialism 1, materialism 2, materialism 3. So we're getting a separate score for each materialism item. Right now, I have not made the scale at all yet. So then what I can do is I can make a new one, compute materialism S for success equals, and by the way, I have that as, if you just put an equal sign in Excel, it'll think you're computing a formula. So I have space equals space in there, or you could start with an apostrophe and that will also work. Mean, and then mean mat 1, 2, 3, 4, 5, because 1, 2, 3, 4, 5 are the success items, and 6, 7, 8, 9, 10 are the success items. And in fact, I've done this by concatenating things up here. You can tell how I've done it, although if you only have a few of them, you could type it in by hand. And then, again, concatenate, string those all together into one string, and put it into, where are we, Excel, where's my syntax file, paste it in here. No, let's try that again. Control C, syntax file, Control V. Right, so now I have something. Now, if I run this on its own, I'll run into a problem. It'll say mat1, it'll run these, and then it'll decide that mat1 doesn't exist yet. So what I want to do, and this is again just thinking through your code, I'm going to put an execute here, so it'll calculate all of those, then execute, then run them, and then those variables, now mat1, mat2 will start to exist. And then when that variable exists, now I can come along and combine mat1, 2, 3, 4, 5 into a single scale for materialism's components. And then I can make, another item. Where are we here? Oh yeah. And I can say, I can even type it out by hand if I want to, compute materialism equals, mean, mat S, mat C, mat H, full stop, don't forget the full stop. And again, I probably need to put an execute in here first so that when it runs that line, these variables exist. And now I have something that which, when I select this all and run it, it'll go bang, bang, boom, and it will spit out a bunch of nicely formatted variables for me. And one of the advantages, the big advantages of doing it this way, is sometimes you download your data and then you compute a bunch of scales and you do some analysis even, and then you find that you've run a couple more people or you mess something up, so you re-download your data, and if you've computed your scales by going through the menus every time and going transform, compute variable, type in a variable named mat s equals, and then mean, and then type these in, you have to do it all over again, because when you downloaded the new data, you've lost it. Whereas if you've saved your syntax, you download the new data file, and then you just select your existing syntax, and you can save, run it, and boom, all of your variables are instantly recreated. And you can save these syntax files, and they just save as a text file. You can open it with WordPad on your computer and edit it directly if you want to. So let me see. Was there anything else I wanted to cover with computing scales? Yeah, and if you're ever not sure how you want to do something, you can always go back to compute scales and then put something in there and then hit paste. and it will pop the syntax here, and then you can work with it and go, oh yeah, that's how you do it, and delete it or copy it and paste it and recreate it and change it around. Okay, so I've covered number 1, checking your raw data. I've covered number 2, computing your scales, which is something where if you've got a lot of them, that'll take you a couple of hours to build all of the syntax and test it and make sure it works. Now you've computed your scales, step 3 is to check them and make sure your scales look about right. Now, in your analytics course, they will have told you lots and lots and lots of tests you can run for all kinds of different eventualities. I'm not going to walk you through all of those again. You can look at your notes, you can find tutorials online. I'm just going to show you the real minimal basics that you want to look for. So the first thing you want to do, and I've got some computed scales here like loyalty, pluck, demand. BESC first was, did they have this scale first? So, I mean, I've tagged this 0 and 1 and 1 and 0, 1 and 1, 1, 1, 0. Is you want to start looking, so one issue is you want to make sure that you don't have any ceiling or floor effects. So you want to go to Analyse, and then about the second option is Descriptive Statistics. And so if you've got something categorical, like were you shown success or failure, then you can look at frequencies, and it'll show you 60% of the time they saw failure and 40% of the time they saw success. And it's worth checking that. I had an experiment where participants were assigned to look at different products, and I had 12 different products, but I wanted there to be about an even number of people who were exposed to each product. And so when I ran the frequency, how many people saw each product, because there was a variable called product, and the codes were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, right? What I found is that there were lots and lots of people had seen a bookstore, and very few people had seen the Wall Street Journal, which was a different. And so my randomization hadn't worked very well, and so I was able to go back and try and correct it and run some more people in the specific conditions I was lacking, because I had checked the frequencies. Now, if you have something that's a scale, so it's like materialism or BESC, where it's a 1 to 7 score, then the frequencies won't be very helpful because, in fact, just for fun, let's do that. Frequencies. The frequency is like how frequent was each given option, and let's run it for materialism. Okay, and what you see is lots of people put 1 for material, and the reason it says lots of people have 1 is because it's hiding decimal places. This is like 1.01, and this will be 1.03, and this will be 1.09, and this will be 1.12 or something. So there's one person who gave each of this, and then there were 3 people who had 3.07 or whatever this is, or 3.25, or so it's not very useful looking at frequencies for a continuous variable. So if you've got a continuous variable, you don't want to know how many times each possible option was chosen. You want to look at data transform for Analyse. You want to look at the descriptives, which is the second option. So let's take the descriptive for materialism. And you can choose several of them, and let's take BESC and subjective well-being, and you can just choose a whole lot of them all at once, and pluck. And we'll see options. What have we got here? Mean, standard deviation, minimum, maximum, but you can choose other things. You can choose kurtosis and skewness. Those are good things to check. Style. Oh, that's auto highlighting your syntax. Don't worry about bootstrapping. And we'll just hit OK here. Now, instead of for every single possible score materialism, it tells you materialism n equals 194, minimum 1, maximum 7. So it was a 7-point scale. BESC 1, BESC 5. So either it was a 5-point scale or it was a 7-point scale and nobody went to 7. But I think it was really a 5-point scale. And it tells you what the mean is and the standard deviation. So it's worth looking at this. Subjective well-being, -9 to 21. Now, you've got to think about this. Is -9 a legitimate score for your scale? Right? So if I saw a materialism scale and someone had scored -9 in it, I would be really worried, because you can't get, that would mean maybe I hadn't reversed items, or I'd done something silly, or Qualtrics had scored it in a really weird way. I would be really worried if I saw a negative number for materialism, because there are no negative numbers in the scale. Like, it's not possible for a participant to check -5. So that would be cause for me to go back and look and find out what went wrong, because if I analyzed it and it was computed in a weird way, I wouldn't be analyzing anything real. I'd be analyzing some weird data gremlin. It turns out with subjective well-being, SWB, you calculate it as positive affect minus negative affect plus life satisfaction, so it is actually possible for someone to get a negative score, so that's nothing to worry about. PLOC is again calculated with adding and subtracting, so it's possible to have negative scores. So you can look at, like, are the minimum and maximum sensible? Another thing you can look for is the mean. Now, it's maybe not obvious until you think about it, but you want the mean to be somewhat close to the middle of the scale. Because if I looked at the mean of materialism, and materialism was from 1 to 7, and my mean was 6 point something, what that would mean is most people were putting 7s, and a couple of people were putting 6s, and nobody was putting really anything much lower than that, because if you have a 1 to 7 scale and a mean of 6, that would mean that you're just averaging mostly 6s and 7s. I mean, mathematically, that's just how it has to be. And what that would mean is you have a ceiling effect. What that would mean is when you try and use materialism to predict something or to be predicted by something, it's going to be really hard to find a significant effect, because everybody's giving you the same two answers. Everyone's saying materialism 6 or materialism 7. Nobody's saying 3, nobody's saying 4, nobody's saying 2. And it's very hard to predict something when there's no variance in it. And I'll give you a quasi-famous example of this. It turns out there's a test that they use for grad school, getting into grad school in North America a lot, called GREs. So you write these GREs and it gives you a score for your verbal, and it gives you a score for math and something else, analytic, I think. If you take a look at PhD students and you look at how well they're doing, and then you look at their GRE scores, you find there's very little correlation. So the ones who are doing really, really well don't seem to have GRE scores that are any different than the ones who aren't doing so well. And you might think that's a bit strange, because in order to get accepted to their PhD program, they had to write these GREs, and then they were selected on the basis of these GREs. One of the things, to accept you to a PhD program, you did really well on your GREs. Well, we should have you in our program because you're smart. So if the GRE results don't really correlate with how you're doing in grad school, does that mean that grad schools should stop looking at GREs? Does that mean that GREs are worthless for predicting who will do well in grad school, so just stop using them? Maybe. But it turns out that there's a little bit of an issue here, which is if you get a really bad score on your GREs, generally you don't get into grad school. So the people who get into their PhD programs are all people who did either sort of well or really well on their GREs. So when you use GRE scores to predict how well people are doing in grad school in their PhD program, what you're testing is, does it matter if you do well or really well on your GREs? And it turns out it doesn't. But if you do really badly on your GREs, maybe then you would do badly in grad school. But we don't have those people in grad school, so we can't see that. We don't know. So if you looked at the people, the grad students' GRE scores, you would see that the mean was fairly close to the maximum, and that would be what we call a range restriction with a ceiling effect. So if you look at your data and you see that one of your numbers is like that, you can go and look closely at your data, and you can go to here and you'll see that on this variable you've got mostly 6s and 7s and that'll be y, or mostly 8s and 9s, or whatever it is. And that is a variable that you're going to find it doesn't predict much. It'll have, and that might mean that there really is nothing to do with it, or it might mean that just mathematically it was measured badly, and that's why it doesn't predict anything much. So you want to look out for, and also if you have a very mean very close to the minimum or the maximum, you'll probably have a very low standard deviation because there's not a lot of variance. Everyone's just giving the same few scores. So that's something big to watch out for. Now, the next thing that you want to look for when you have scales, where are we, Analyse, is you want to look at their alpha. So you'll find it under Analyse, Scale, and the first option is Reliability Analysis. So again, you can find variables and put them in here. But with the reliability analysis, you don't put the finished variable scale in here. You put the items that make it. So you'd have materialism 1, materialism 2, materialism 3. You'd put those in here. And then the statistics you can look at here. One of the useful ones to have is scale if item deleted. And I'll show you what that does in a second. Continue. Again, I'm not going to press OK, I'm going to press paste. And that will have, if I look at my syntax file over here, right, there you go, here's the command. Reliability variables equals these 4 different variables. Scale all variables, model alpha, summary, total. So if I select that and run it, blonk, blonk, here I am. And so it's cases, there are 186 valid cases and 8 excluded cases. It has list-wise deletion. Right, so there were 8 cases where they were missing data on at least one question, and so they've been eliminated. So it tells me my overall alpha for the scale is 0.730, which is okay. Not great, but okay. It's passable. One of the things about alpha, one of its quirks, is the more items you have, the higher alpha tends to be, all else equal. So if you have an item with scale with 15 items, it'll tend to have a higher alpha. And then you've got this table down here. Because I asked for if item was deleted, it's produced this extra output. So it says the scale mean if this item is deleted. So this one must have quite a low score, because if I deleted it, the mean would go up quite a lot. Scale variance, corrected item total correlation. But this last one here, Cronbach's alpha if item deleted, is sometimes worth looking at. So if I deleted the first one, the alpha for the scale would go from 730 to 734. Wouldn't make much difference. If I deleted the second one, it would go from 730 to 563. So clearly this item block identified is doing a lot of work to get the item mean to where it is. And sometimes what you'll see is if you've got something with mediocre alpha, there'll be one item where if you delete it, the alpha gets much, much better. And then you might think that that item is worth getting rid of. Or at least you can make an argument that perhaps you should, because it's not predicting the same thing as everything else. Or maybe it's measuring it badly. Or maybe it's adding a part of the variance that really should be there. But that's something that you have to put your thinking hat on and understand what you're measuring and understand the questions that people are answering and understand what's going on in their heads and are the answers that they're giving you lining up with what's in their heads. So you'll want to compute alpha for your different scales. Let's think. Then another test that you'll want to run for your scales, especially your bigger, more important ones, Analyse, dimension reduction, factor analysis. This is an exploratory factor analysis, or EFA, where you don't tell the computer what dimensions to use, you just let it work out what it should be. So I'm going to pick these 4 items here, the clock items, descriptives. Yeah, that's fine. There's a couple of things that you want to work at here. Extraction. So right now it's doing it based on eigenvalues. Sometimes we'll come back to that. Here's the one you definitely want to check. You want to do a rotation. Varimax is the most popular one. And for our purposes, we'll just leave it at that. Pure methodologists would be having a heart attack if I told you to just always do a Varimax rotation, but there are no pure methodologists here. So continue and scores, the options. There's a really handy one here, suppress small coefficients. So I usually do it below about 0.4. Continue, it just makes the table easier to read. And then I'm going to paste. We'll paste it again because that means we can always recreate our analysis later. Here we're doing, okay, and we will select our factor analysis and we'll run it, see what happens. Boom. Right, I mean, this is a scale with only 4 items. So it's of somewhat limited interest. Make that thing go away. So the things to look for as a real crash course is communalities. How many factors? So the default option is it computes these eigenvalues and it'll compute 1 factor for every component that has an eigenvalue of greater than 1. So this is just SPSS guessing how many factors to have, taking an educated guess. And in this case, it picks out 2 factors, which it turns out is actually the right number. But oftentimes it will get that wrong, and so you'll want to you'll look at the component, you'll look at the solution it comes up with, and then you'll say, yeah, but what if we add a factor? What if we add a factor? And then you'll go back to analyze, and where are we? Dimension reductive factor, and then you'll say extraction. Okay, don't just go eigenvalues greater than 1. Give me a fixed number of factors. Give me 3 factors. Okay, continue, and then okay, let's see what that looks like now. Okay, now I'll come back to the one I did with 2 factors here. So the first one is the unrotated matrix, and the short answer is just ignore that. Look at the rotated matrix, and the reason there's missing values here is I told it to hide anything that's less than 4. So this number is probably 0.2 something, and this is probably 0.3 something, or minus 0.3 something. But I said don't show me anything that's less than 4. And so what I see is that clock intrinsic and identified load on 1 factor 0.94 and 0.84, and clock introjected and clock extrinsic load on another factor 0.876 and 0.900. And if you know how the clock scale works, then you are very happy because that's exactly what should have happened with that scale. It's supposed to have an intrinsic component with these 2 items and an extrinsic component with these 2 items. And often when you do a factor analysis, especially if you have lots of factors, so like in materialism there's 3 factors, and in some other scales there's more. And especially if your sample size isn't enormous, you can get quite a bunch of bounce and gremlins. And so here's when I force it to say 3 factors, it picks out 1 for intrinsic and identified, and then it forces extrinsic and introjects it onto separate ones. So you can toy around with that with your variables, and you can start to get a sense of the shape of your data, which is a strange thing to say, but when you start playing with data, you'll see what I mean by it. One warning is, especially if your sample size is, less than 200 or even 300, don't overinterpret. If one item loads a bit in the wrong place, or one item loads on 2 variables when it should just load on 1, that might be a problem with the factor structure of the data, or it might just be that you've not got enough sample size to get a completely consistent, coherent solution, or that your participants weren't paying enough attention to really discriminate these fine gradations that are there in your questioning that they just didn't pick up. So if your sample size isn't staggering, and you've got a factor analysis with like lots of factors in it and complicated things, and it doesn't come up quite perfectly, just don't panic, because factor analysis does have a certain amount of bounce in it, right? This is just the computer looking at numbers, columns of numbers, and trying to find where they clump, and trying to find variables that clump together. And if they don't clump quite right in some small way, that can throw things off a little bit. So it's a useful thing to look at, but don't overly panic or overly interpret it, especially if your sample size isn't huge. Right. I'm going to show you a really interesting trick I discovered. Because if you remember, one of the problems you run into is you run a bunch of participants, but some of them pay close attention and answer each question carefully. And some of the time, some participants just start going through and just clicking like numbers to get through your survey. They start going 5, 5, 6, 6, 6, 5, 6, 6, 6, 7, 5, 6, 6, 6, 6, 6, 7, 5, done. Okay, good. Haha. I'm finished. I've given my data. I can move on with my life. So what I found, and no one that I know of has published this, but it's a trick I found actually works pretty well. If you have a scale like materialism, materialism works, but any scale where some of the items are reversed, but you otherwise have like a pretty good alpha, what you can do is compute scores for each of the items where they're reversed appropriately. So materialism 1, materialism 2. So the items are. Then what you can do is you can go through and you can make an average of all of the items which are not reversed. But I'll get rid of that one. Yeah. So you compute a scale, and I'm just sort of clicking on Excel here instead of computing, right? And so you compute one scale, which is all the not reversed items, and a second version of the scale, which is all of the reversed items. And it doesn't matter if they're in different facets, so long as the scale has a good overall alpha. And then you take those two numbers and you subtract one from the other. It doesn't matter which order you do them in. And what you find is that if people have been paying attention, then those numbers from the reversed items and from the not reversed items should all be about the same. So if they were giving 5, 5, 5, then when they got to a reversed item, they probably gave like a 2. And then when they got to a not reversed item, they gave a 5. And then a reversed item, they gave a 2. If you reverse those, then you should see just 5s and 6s and 4s and all the way down the line. And so when you take an average of their reversed items and their not reversed items, you should get a score that's around about 0 or not far off 0. But if they were just kind of clicking through and not really paying attention, they went 5, 5, 5, 5, 5, 5, 5, 5, 5, and then they got to reversed items and they were still clicking 5. So when you reverse it, that 5 turns into a 2. And then, so if they've done that systematically, and they've given sort of like 4, 5, 6 to everything, 4, 5, 6, 4, 5, 6, 4, 5, 6, when you reverse the items, their not reversed items have an average of 5, and their reversed items have an average of like 2. So 5 minus 2 gets you a score of 3. And what I find is, if you calculate it that way, the people who have scores of 3 and 4 on this scale, when I have like another question in there that like captures were they paying attention, the people who have 3 and 4 on this scale, they're the ones who get who fail the manipulation checks items. So I mean, I had an item where I asked them, questions that there was an objective right answer to, like, is a Converse high top a branded item? And the answer is yes. And if you write, no, it's not branded, you're just not paying attention, you're not thinking it through. So I have a couple of questions like that. And what I find is the people who get those questions wrong, where there is a definite right answer, they're the ones who have this big spread on materialism between their reversed and their not reversed answers, because they weren't paying attention when there was a reverse. They didn't give low answers to the reverse items and high answers to or vice versa. So this is a little trick that you can do, and so you compute this score, and if people have got 3 or 4, if people have got really high scores on this, then you just exclude them from your analysis. You say, these people were not paying attention, I shouldn't interpret their numbers, because the numbers they gave are just junk. It's just them clicking on numbers and not reading my questions and thinking about what they mean and giving an honest answer. So I hope my explanation there is clear enough. It's completely clear in my head, and hopefully I haven't confused you by just describing it with words. And if not, then don't worry about it. It's just a nice trick that you can pull off. Okay, so number 1, I told you about checking your raw data. Number 2, talked about computing scales. Number 3, checking your scales, ceiling effects, alphas, factor analysis. Number 4, analyze the data. So once you've got it all sorted out to your satisfaction, and I mean, in your analytics course they told you about lots of tests I didn't tell you about here, and you can by all means go into those and clean your data even more precisely. There are, let me think about this. In all of statistics, there are only ever 2 questions. There's a million different tests you can do, but really only 2 questions. One of them is this set of numbers higher or lower than another set of numbers? And the other question, question number 2, is, does this set of numbers move together with another set of numbers, or does it move in an opposite pattern, or does it move in an unrelated way? And the reason you've got a million tests isn't because there are more questions than that. It's just because our statistics aren't very good. Our math isn't very good, and so depending on, we can come up with, if you make a bunch of assumptions, I can come up with some mathematical operations that will test whether this set of numbers are different than another set, but if those assumptions aren't quite right, then the test doesn't work anymore, and then I have to come up with another test that will fit that pattern of numbers. So this isn't because that's how numbers are supposed to work, it's just our math isn't very good. So when you want to say, is one group of numbers different than another, that's where you want to run a t-test. So if I look through my variation, I have, let me see, gender. Gender is something where I have 1 and 2, and if I've downloaded, if I labeled it correctly, 1 would show up as male and 2 as female, or vice versa. I don't know. I'd have to check which way I put it. But I can go to Analyze, compare means, and independent samples t-test. So one sample t-test is the average of gender different than, in fact, let's do it. Gender, and there's a test value of 0, and so it's going to test, is the average gender score different than 0? And it will be, because if you look at it, every single answer is 1 or 2. So maybe I'll even put a test value of 1.5 in here, because if there's an exactly equal number of men and women, the average score should be 1.5. That's okay. Take a look at this. And what we find is mean is 1.43, which is slightly lower than 1.5, but is it significantly different than 1.5? And the answer is T significance 0.057. Normally our criteria for significance is 0.05, P less than 0.05. So I reject the null hypothesis, and I accept the null hypothesis. Sorry, and I would say that there probably is a fairly even split of men and women here. Analyze, but if I want to compare, let's say, do men and women have higher materialism scores. Okay, where am I? Compare means independent samples. So men are one sample, women are the other sample, independent samples. So I need a grouping variable, which is who are my groups of people, and that would be gender. Whoops, gender. My test variable, I said materialism, right? So are men more materialistic than women? And we can put a couple of them. How about BESC? Are men and women different than BESC? Oh, and I have to actually tell it what the groups are. So group 1 is 1, 2. You can also do it with a cut point. So anything higher than 1.5 or lower than 1.5. But I'll do it with my specified values, 1 and 2. Continue, and now I could go paste and save. Well, I just have paste. Here we go, t-test. By the way, when you have your syntax, sometimes when you're creating the syntax, you know what everything means, but then you look at it a week later and you forget why on earth did I write this. You can write comments. So if you put an asterisk or a star, this is a test of something, and then a full stop closes the line. When I select that line, it does nothing, because SPSS says starts with an asterisk, ends with a period. It's just a comment. So you can write lots of notes to yourself about what you found. You can make visual barriers in it. You can say, okay, main analysis stuff here. Wee. So that when you look at it later, you go, oh yeah, this is where all these analyses are. So anyway, let's run this now. Bonk. So let's see. Materialists. Oh, we got 111 gender 1 and 81 of gender 2. So 111, I think, men, 81 women. And there's the mean is 3.89 for men and 3.82 for women. So that's within 0.7. That's probably going to, or 0.07. That's not going to be significant. And if you look down, sure enough, 0.85. It's not. For BESC, mean 2.79, 2.83. That's very similar numbers. And again, yep, that's not significant, 0.902. Oh, that's the test of equality of variance. In your analysis course, we'll talk about the significance for the equality of the means. Do they have the same mean? Significance 0.699, 0.803. I mean, again, not significant. And then you have confidence intervals. So it seems to be between minus 2.79 and 4.16. It's a 90. And so 0 fits in the confidence interval, so you can't conclude that your answer is different than 0. So it looks like with materialism and BESC, there's no difference on gender. So you've got group 1, group 2, and how is their score on something different than something else? That's a t-test. And so sometimes you'll have tests like that. How is group 1 different than group 2, or group 3 and 4 and 5? And that's where you have ANOVAs. So that's test 1. I told you I'd tell you about 3 main tests. Test 1, t-test. Next one, correlation. This is a test of, are these numbers moving together? Are they not? So analyze, correlate. You are going to be doing bivariate correlations. There are other kinds, but for your purposes, we're sticking to bivariate. Bivariate just means 2 variables, bivariate. Okay, and so I've already put in some variables here, PLOC and BESC. And materialism, you could put in more, you can put in less. You can put in as many as you like. Options. Exclude cases pairwise is actually a good thing to have, because that says it'll only exclude a case if it's missing data for one of those 2 variables. But if it's missing data for, if someone's missing data for materialism, but they've got values for BESC and PLOC, it'll still tell you what the correlation is, including them on that test. It will just skip it when materialism wants. Okay, continue two-tail test of significance. And again, paste. Blah, blah, blah. Right, correlations, plot, and you can even type in other variables here and say, give me hole in trim or something. So you can cut and paste this and add type in variables and delete variables and move them around as much as you like. So let's look at this correlation matrix. So you've got the matrix and it's the same on the top as on the bottom. You've seen these before, I'm sure. So Plock and Besk, not really correlated, 0.095 is their correlation coefficient, 0.197 not right. Plock and Materialism, really not correlated, but Besk and Materialism, 0.387, and that's typically what you get. They tend to correlate sort of 0.380, 0.440, 0.450, that's typically what you get for Besk and Materialism. Let's add another one in. So let's go, correlate bivariate. Let's add in subjective well-being. Well, okay, because we know that, I mean, people have for years and years said that materialists are less happy than other people, but what about those who are high in Besk? Let's run that, and then don't you know it? Yeah, materialists, minus 214. Yeah, so they're less happy, and people who are high in Besk are actually more happy. That's interesting. Let's add another variable in here just to see what we've got here. Loyal, right, so are you more loyal to your phone brand if you're a Besk or a materialist? So let's see, Plock, people who are high in Plock are a bit more loyal. People who are high in Besk, 0.403, they're really loyal. Happy people are more loyal. Materialists, not so much. Well, it's interesting. Yeah, you would have thought that they should be in it. In other data sets, they often are a little bit with materialism, but not in this one. Okay, but let's look at this a little bit. So we know that people who are high in Plock okay, so yeah, let's do kind of something interesting. So look, we know that people who are high in Plock are happier, and they're also more loyal. But we also know that people who are happier are more loyal too. So are they happy because they're high in Plock, or are they happy because they're high in loyalty? Right, so you've got, let's say that our dependent measure, our outcome measure is loyalty. We're interested in who's loyal to products. And we know that 0.28, people who are high in Plock are a bit more loyal, and also that people who are happier are more loyal. But we also know up here that people who are happier are also higher in Plock. So maybe it's just the overlap between those variables, and you can think of it as like a Venn diagram. On its own, correlation will never ever sort that out for us, because correlation is just one variable and another variable, and then one variable and another variable. It just looks at the pairs of variables in total isolation. But what we need to know is not, we need to know what happens with these two predictors if you use them at the same time to predict an outcome. And can you separate out their overlap on this outcome? And this is where you analyze, regression, and for your purposes, linear. We'll do you. I mean, there's a lot of different kinds of it, but for our purposes, linear regression is all we're going to use. So we can have one variable as an outcome variable, a dependent variable. And then, well, let's start off, first of all, I'm going to do only Plock. So you have one independent variable and one dependent variable. And I'm just going to, well, let's paste it. Get used to using paste, right? So here's our command here. Variable missing listwise, right? Dependent, loyal, method, enter, plock, and that's our independent variables. So first we'll run this and see what we've got. So sure enough, we find blah, 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 blah. The overall table is significant. Plock, standardized coefficient beta, 0.282, significant 0.000. Now, if you come back to this correlation coefficient, loyalty and plock 0.282, 0.000, it's the same number. It's the exact same number. Here is one of the insights. A regression with one independent variable is exactly, mathematically, exactly identical to a correlation coefficient. It's the same test. Not even close or similar. It's literally mathematically identical. You'll have exactly the same coefficient and exactly the same significance level. So sometimes I see students and they'll do correlations between two variables, and then they'll do a regression where one variable predicts one outcome variable, and they'll say, now with regression, it's still significant. And you shake your head because what they've done is the exact same test twice, and of course it gives the same answer. It's the same test. But what regression will let us do, that correlation will not let us do, is regression. Well, in fact, let's do it with syntax now. We can add in more than one. So let's have plock and subjective well-being. And run this. Boom. So now all of a sudden we have plock and subjective well-being simultaneously predicting loyalty, dependent variable loyalty. And what we find here is plock 194 and subjective well-being 120. Those are the unstandardized coefficients. For our purposes right now, we'll stick with the standardized coefficient because it's easier to compare with a correlation. 0.205 for plock. Let's come up here. Plock is perceived locus of causality, for those who care. Plock and loyal 282, and here it's dropped to 205 from 282. This one, it's plock and subjective well-being is 335, and up here subjective is 382, dropped to 335. So what you're seeing is the coefficients are no longer identical. They've gotten smaller, and the reason they've gotten smaller is because each of those variables, part of them uniquely predicts the outcome variable, but part of them predicts the outcome variable in common with the other one. And so what the regression is trying to do is it's trying to say, okay, this part that you predict the outcome variable in common, we're just going to divide it up, and we're going to try and figure out who gets credit for that shared variance, and then we'll give you most of that credit. And so what you see is these numbers shrinking, and so sometimes you'll have a significant relationship in the correlation, and then when you put it in the in a regression with another variable that's more strongly related to that dependent variable, it'll drop to nothing. And what that's telling you is you've got probable mediation. Now let's do one more. Let's do. We'll keep loyal as a dependent variable. Instead of plock and subjective weighting, I'm going to do materialism and best. And we'll run this, and we'll see how this goes. Now, materialism, negatively related to loyalty, BESC, positively related. So let's see if we can remember these numbers. Let's compare it to the correlation coefficients. We've got 497 and minus 246. There's our correlation coefficient. Here we go. So 497 for BESC, 403, 387 for materialism. It's gotten smaller there too. In fact, actually, it's gotten a bit bigger because
you've got a suppression effect. Now let me see, materialism block. Let's try it again. This is what I was thinking of, materialism block. Let's have materialism and block one more time. I'm going to try this, linear block and materialism. Let's add that in. This is an interesting one to do, and you'll see why in a second. So loyalty being predicted by materialism and block, okay. Materialism minus 0.055, block 282. Materialism and loyalty, where are we? 0.055. And block and loyalty, 282. So you see those numbers are actually the same, 282 and 0555. Why is it that they didn't drop there? Every other time we had two predicting the same thing, the coefficient was dropping because it was dividing up variance between them, but here it hasn't dropped at all. And the answer is, if you look up here, the correlation between materialism and block is minus 0.001, which is basically 0. So there is no overlap between materialism and block, just none at all in this score. So when regression tries to sort out the overlap between them, their common explanation they have of loyalty, there isn't any. There is no variance that's shared between them. There is no in common explanation. It needs to be divided up. So it says, it's like having, in that case, a regression is like having two independent correlation tests. There is no overlap to adjust for, so it gives you the exact same answer pretty much over again. So that is my crash course in regression. Now, there's two wrinkles that I'm going to cover now, and then we're going to call it quits. The first wrinkle is some of you have tests of mediation. So variable A causes variable B, and variable B causes variable C. So you can do correlations, and you can show that variable 1 and 2 are linked to each other, and variable 2 and 3 are linked to each other. But if you want to test the mediation, you want to open up, let's find a browser. And we are going to search for Sobel test. The first hit is the Sobel test calculator. Calculation for the Sobel test. And there's some way to the wise, only works well for large samples, remember. If you have raw data, bootstrapping up is a much better. So it's not the exact best best way of doing it. There are better ways, but for our purposes, this will be our test of mediation, right? And so here's a mediation diagram, IV, mediator, DV, and the direct effect between them. And this web page gives you, instructions on how to get numbers. Run a regression analysis of the IV predicting the mediator, and that gives you A and SA. And there's a little table that you can fill in here, A, and then the standard deviation of A. And you can type in numbers here like 0.231 and 0.012, and these are numbers you would get from running a regression. And then you run another regression with the IV and the mediator, both as dependent variables predicting the DV, and that gives you B. I'm just going to make up fake numbers here, 0.339, and SB, which is the standard error of B. And there's a bunch of links that try and tell you help you get them from the right things, and we'll call this 0.082. And once you've entered those four numbers, you hit calculate, and it gives you the Sobel test, p-value 0.003. So that's a very, very significant mediation score, which doesn't mean anything because I just gave fake data, but you would have real data you could put in here and you could get tests of mediation. Okay. For moderation, this is where you have an interaction. Close all tabs. Moderation is trickier because moderation, there's a couple of steps to follow. Now, if you Google it, you will find web pages that give you advice, that give you a walkthrough and show you how to do it, and also show you how to plot out the answers. And I highly recommend that you do that if you need to, because then you can get a walkthrough. But really quickly, before you can, before you do a test of interaction, let's go to, where's our thing here, right? So, if we have a regression with materialism and BESC predicting loyalty, and we're predicting an interaction, we need to have materialism and BESC entered into regression, and also a term that is the interaction between them, which you can call mat times BESC. Now, the problem that we first face is that that variable doesn't exist right now, so we have to calculate it. And the way you calculate it is you say compute materialism times, maybe we need to call it mat times BESC equals mat times BESC. Don't forget the full stop. The full stop's important. Execute. And if I run that, bonk, it will have created a variable, where are we, called mat times BESC. Now, there it is. Now, you're seeing some very big numbers here, 12, 18, 21, 23. That's because you're multiplying something with a 4 times a 1 and something with a 5 times 4.2 or something. It's actually, you can run the test like this with this variable, but the numbers are very hard to interpret. It's much easier to interpret if you center the variables first. So what that means is you need to center each variable around 0. So one of the things about correlation and regression is if I compute a new variable, let's do it right now. Compute a new variable, and we'll say mat plus 400, and we'll compute this as materialism plus 400. Whoops, 400. So every single materialism score is just added 400 added to it here. If I go analyze, correlate bivariate, and let's add in to this test we had before, we'll add in this new mat plus 400. Okay, and what you see is that materialism plus 400 correlates 1.000 with materialism. Adding a constant to a bunch of numbers it doesn't change the correlations at all, and its correlation minus 0.01, minus 0.01, 0.387, 0.387. You can add numbers, you can subtract numbers, you can divide, you can multiply by anything, because correlation looks only at the relationship that those numbers have with each other, and that relationship doesn't change. A 5 is always bigger than 2. Even if you add 100 to both of them, it becomes 105 compared to 102, but it's still 3 bigger. So you can do these linear transformations, but what we're going to do here, instead of just adding some random number on, is we're going to go analyze, descriptive statistics, get the descriptives for materialism and BESC. Who cares about that other stuff? Okay. And we need the means. So materialism 3.85, we're going to now compute mat-centered, and we're just, I even call it that, I mean the mat-c is fine, equals materialism minus, let's find what this number is here, mean 3.85. And compute BESC centered, I'm too lazy to write out centered the whole way, equals BESC minus, and what's the mean of BESC? 2.8. And then we'll execute those. And then we can compute mat times BESC. And instead of mat times BESC, we will use mat centered and BESC centered. You've got to remember what you called them. And when we run this now, bonk, we get, it tells us it's run it. And if we look at our data, right, so now our mat times BESC, instead of being 23 and 5, it's 0.13 and 1.85 and 2.1. So now it's essentially on the same scale as materialism and BESC score. So now we can come back to our thing. Let's move this underneath here. So it doesn't really matter, but just so that we can remember what we did later, you can see that we did the second. We've got our regression with loyalty and materialism BESC, and materialism times BESC. That's our interaction term. And we'll run that. Now our regression, we've got our constant, 4.8689, and that just means it's different than 0. It's not a big deal. Materialism, minus 4.35. So it's actually negatively predicting loyalty now, and that's because it's having a complicated suppressor effect with BESC. We won't go into that now. You can read about that some other time if you want to. Minus 273, we'll use the standardized coefficients, minus 235. BESC 503, and this standardized coefficient, the interaction term, mat times BESC, 0.108, turns out it's not quite significant, 0.104. But if that was significant, if that was 0.02, p less than 0.05, so 0.02, 0.01, something like that, that would mean that we have a significant moderation effect. That would mean that the effect of materialism on loyalty is different depending on your level of BESC. So in this data, we would not support that conclusion, and we would conclude that you just have independent effects of the two of them and you don't have an interaction between them. But if that was significant, then you could conclude that you had significant moderation. Now, interpreting what that interaction looks like, the way you do it is you plot out the regression equation and you put in hypothetical values. So just to show you really quickly, if you look at the unstandardized coefficients here, your regression equation for mat and BESC and the interaction between them, your predicted loyalty score for any given person would be 4.679 minus 0.435 times whatever their materialism score is. So if I scored 7 out of 7, then it's minus 0.435 times 7 plus 1.044 times my BESC score. So if my BESC score is 2, then it's plus 2.088. And mat times BESC plus an interaction score. So 0.162 times my materialism score of 7 times my BESC score of 2, and if you multiply all that out, that'll give you some number. So if you add all those up, 4.679 plus minus 0.4535 times 7 plus 1.044 times 2 plus 0.162 times 7 times 2, and you add those numbers all up, and it sounds like a lot, but keep in mind this is like high school math. This is something that you were doing in your second year of high school. It's like a really short equation. Like you multiply out the numbers and then you add them up. it sounds like a lot, but it's actually very easy. That would give you a predicted loyalty score for someone with that level of materialism and that level of BESC. And so if you're going to plot it out, you would make a hypothetical person with high materialism and high BESC, and you'd work out what their predicted score is, and then you take another person, hypothetical person with a high materialism score and a low BESC score, and another hypothetical person with a low materialism and high BESC, and then another hypothetical person with low materialism and low BESC, and for each of them you would plug in values into this equation and get a predicted loyalty score, and then you just plot that on a little graph and connect the lines, and that gives you a visual that you can interpret. And I leave that as an exercise for you to work out, because it's hard to show on the computer here, but you can do it in Excel. You can have Excel do all these calculations for you, and if you will find web pages that will even give you a little Excel script that will do it for you. And that is how you test moderation. So that's all I'm going to tell you about today. But to summarize, finally recap. Step 1, checking your raw data. Step 2, compute scales. Step 3, check your scales. Step 4, analyze. And under analyze your data, we had t-tests for differences between groups. We had correlation, looking at individual pairs of variables. And by the way, correlation works okay with dichotomous data. So if you've got something where the answer is yes or no, or threatened and not threatened, or successful and unsuccessful, and so you've given a score of 1 and 0, or 1 and -1, correlation will work just fine with that. Correlation does not work as if you have multiple, so if you have red, yellow, and green, and red is 1, and yellow is 2, and green is 3. Correlation will assume that you mean that 3 is higher than 1, but with red, yellow, and green, it's nominal, it's categorical data. It doesn't make any sense to analyze it that way. With regression, it's like correlation. It's okay with 1 and 0 dichotomous variables. With more than 3, with 3 or 4 or 5 levels, there is a way to do it, but it's more complicated, and we won't go into that now. And then if you have mediation Sobel test, which you use regressions to build, and if you have moderation, or if you're testing for moderation, then you need to test for interaction effects. So that's all I want to tell you about now, and I will sign off and let your head spin quietly on your own.